Thanks, Eleni, and all the organisers for giving me the chance to speak here today. So I'm going to be talking about some work that started with Peter Turner in the University of Bristol, and since we've expanded on mostly with my shared PhD student Rawad Mazet, who's sitting at the back, and Joe Galbouni and Joseph Trim at the Lebanese University. And so this is kind of a bit of a shift from the previous talks towards quantum information. But so hopefully some of the ideas and techniques here are useful and have applications towards the broader theme of this workshop on measurement and control. In particular, they have known applications for benchmarking. Okay, so this work is about, so what do we mean by unitary designs? It's a way of sampling unitaries in a random way that is useful for various applications that I'll talk about. Okay, so in particular, there's many results similar in feeling to what's used in information theory, where it's shown random codes, for example, are going to be good codes for information processing. Across physics and quantum information, it's known that randomly choosing a unitary from the set of all unitaries in the right way is useful for a bunch of things. And the right way is typically mathematically conveniently written in terms of the Haar measure, so with relations to the averaging over the group of all unitaries. Okay? So it has, for example, application in kind of most clearly in hiding information. So if I apply a randomly chosen unitary from the full set of unitaries, if you have no information about which unitary I've chosen, your system looks totally random, so it looks like the identity. Okay? Another application of these random unitaries has been in kind of closer to the theme of this workshop is in benchmarking. So if you have a channel, gamma, that you want to know something about, if you send a system in it to which you've applied a random unitary and undo this unitary on the outside, it allows you to probe this channel for certain pieces of information, in particular if it's doing the kind of circuit or gate set that you want it to do, in an efficient way. Okay? So this is what people call benchmarking using these randomly chosen unitaries. It can be used for checking entanglement. So entanglement is a really significant, important resource in quantum information. So for example, if I take the singlet, the maximally entangled pair, this is the only state that's invariant under U tensor U dagger for all U's. So if I randomly choose a unitary from the full set of unitaries on a single system, then the only state which will be unchanged all the time is the singlet state. So this is the kind of idea behind using these random unitaries for testing entanglement. Okay? So another kind of more recent in the last few years application that I'll be talking more about later as well is in demonstrating what's called quantum supremacy. So if you take a unitary from a sub-universal or even from a universal set of gates randomly from all possible circuits, then you can show that with high probability the statistics that you'll get at the end will be hard to reproduce efficiently with a classical computer. And this is what's sometimes called quantum supremacy, and what's kind of the idea behind these boson sampling and IQP, or instantaneous quantum polynomial, are instances of this family of problem. So again, we see that these kind of being able to randomly sample from a unitary in this application allows you to show something as what's going on in your boxes here is something quantum. So these are kind of, I guess these two here, this demonstrating quantum supremacy and this benchmarking, are what's really kind of interesting for the quantum computing community in order to check that their devices are doing something really that's better than quantum, better than classical, or doing what it is that you want to do. Okay? So we'll look more a bit about those. Okay, so this sounds great. So what are the kind of questions that are important in doing this? Why do I need to, well, I'll present as some new techniques for doing this and some new applications that come from these. So why do I need new techniques if these results are all true? Well, the first is that sampling from the Haar measure, so all of these results are kind of very easy to prove, well, very easy to prove. The typical techniques use a lot of group theory and beautiful group theory and Shor's lemma, which come from the fact that you're sampling from the Haar measure, okay? So, however, experimentally or trying to implement these requires an exponential number of gates and random bits. So this is somehow, if we're thinking about kind of trying to do efficient quantum computation, for example, or any kind of application in quantum information, then this exponential gates and random bits is not going to be very interesting for us, okay? So that's the first problem that we come across here, which was noted by Knill in 95. And then the second problem that we want to kind of address in this work is the practicality of generating these random circuits, okay? So even if I've got a way of generating my circuits in a nice, what we'll call efficient way, I have to be able to implement these. And if I'm randomly choosing from a set of gates, which we'll talk about soon, that translates to having to randomly choose or adjust your experimental apparatus, and that's something that we'd like to avoid. Okay, so, oops. So the two kind of main goals that we have here in our new way of sampling from random sets of unitaries are, first of all, what we'll introduce next is these so-called T-designs. So these families of unitaries, which are not kind of an infinite family of unitaries like the Haar measure, and somehow they can be efficiently sampled from. So they mimic these kind of nice properties of the Haar measure up to some figure of merit, which I'll describe on the next slide, in the right way. And our second goal here is to use kind of what we call a measurement-based picture to generate this randomness, okay? So this is going to allow us to, instead of having to adjust our experiments according to our classical random parameter, is going to allow us to take a fixed experiment, and the kind of randomness, if you like, of your quantum measurements is what's going to give us our random sampling, okay? And so this allows us, for example, to have fixed states followed by fixed measurements, and in the circuit picture it's going to correspond to constant depth circuits for these things. Okay, so what is a unitary T-design? So this is a bit of a technical statement, which is basically the idea is this thing simulates sampling your unitaries from the Haar measure in a way that's useful. Okay, so the usefulness essentially is this. So imagine you have a box which randomly samples from some ensemble PU UI, okay? And into that box you're allowed to put a state row of any T system. So each of these systems passes through these and gets a unitary applied to each of the systems. And so what I get at the output of this, okay? So we call it a T-design if this output is indistinguishable from the output when I've done the same thing on a Haar, on a unitary that's randomly sampled according to the Haar measure, okay? So this is what the T in T-design means, and technically that means it's a Tth order, it's equal to the Haar measure up to Tth order polynomials or tensor products, okay? So that's what this guy we define is, okay? And so mathematically we define it in this way. So this guy, we define it on the expected outcome of this, of these two boxes, right? Because each of these is randomly sampling from a unitary, so I'm interested in what the average case property is like. So I take the expected outcome here, and I take the expected outcome of this guy, and I somehow want to quantify how close these guys are, okay? And that's the idea here. So if I say, if an ensemble is an epsilon approximate T-design, it means that its average output is close up to this epsilon to the Haar measure output, okay? Okay, so that's my definition. So why is this a particularly useful definition? Well, it's known to have a bunch of applications, in particular for low T. So here you can see that there are, if I take T equals 1, the Pauli operators do that for you. So randomly applying a Pauli operator, this is essentially, well, I mean, the Pauli is just an operator basis over my space of operators. But this guy is essentially applying like a random key to a random quantum key. If I take the Clifford group, this is actually known to be a 2 and a 3 design, which is useful for benchmarking. So if I randomly take from these 3 designs then I can have efficient benchmarking. And as I go to t=4, it's known that this plays a role in simulating thermalisation. So if I want to, we'll talk about this again later as one of the applications of our results, is that if I have a system and I want to somehow simulate, so again, this is kind of related to the notions of measurement and control. If I want to simulate the process of thermalisation, if I'm randomly applying a unitary from a 4 design, you can show that this is kind of efficient, this is a good way of modelling what happens in thermalisation. So one of the applications we'll see at the end is a kind of model for a simplified model for scattering, which does exactly this. Okay. Okay, so there has been, in this work by Brandau, Horodecki and Harrow, in 2012, they proposed an efficient scheme, an efficient construction for implementing these T designs for any T and any number of systems N and any epsilon. Okay? So the thing that we're going to do, first of all, is we're going to, however, their construction, which I'll introduce in a moment, relies on inputting classical randomness and using this to construct your random circuit, which would mean that if I wanted to implement this experimentally, for every choice of unitary, I have to redesign my experiment, which is exactly what we want to avoid. Okay, so the first thing that we do is kind of, we come up with a scheme where we sample from a set of unitaries which are, again, have this property of being an epsilon approximate T design, but in this measurement-based picture, so I've got a fixed experimental setup that I do, and all the randomness that's introduced is introduced by these measurements. And along the way, we see that we can find some new designs. So it's actually very hard. These are about all the designs that we know. So when I say design, it means an ensemble of unitaries which simulate the Haar measure up to the appropriate T. And so these are essentially the only ones that we know, and they've got these kind of nice group theoretic properties. But to go to higher designs, we're a bit stuck in how to do so in the exact case. That's why we're kind of forced to take these epsilon approximate designs. Okay, so what we see along the way is we find a new 3 design, which kind of suggests possible approaches to looking for new higher designs. And we see that we can find this in a regular structure. So what this will mean at the end of us, kind of experimentally, it means that I can implement this in some kind of regular, easy to design 2D lattice for my experiment. And in terms of circuits, it means I can simulate these in a finite depth quantum circuit. Okay, so the main idea behind these, our approach, is to is essentially to use, as I say, using measurements in is taken from quantum computation or teleportation, where if I have an entangled system and I perform a measurement on one side, depending on the result of the measurement, I can get different unitaries applied to this. Okay, so in teleportation, if I measure one side, I measure Alice wants to send the state psi. She performs this Bell measurement over these two, and depending on her result, Bob's system will be in the state or some Pauli on that state. And so this randomly samples from the Paulis, which is a 1 design. So our technique is essentially a kind of extension of this, which will follow the construction of an epsilon approximate T design. Okay, so the kind of starting point, and moreover, our kind of techniques will really stem from what's called measurement-based quantum computing, which is like for those of you who don't know, measurement-based quantum computing is just a translation of the circuit model for quantum computing where all my evolution is done by a measurement. Okay, so in really like a generalization of the teleportation. So if I started with a bigger, different entangled state and I perform measurements, instead of getting the Bell operators, I can choose any unitary that I want. And kind of this example kind of encapsulates how that happens. And it starts off and allows us to introduce what's called these graph states. Okay, so this whole framework of measurement-based quantum computing that we're going to use for generating these ensembles of unitaries, these T designs, can be kind of understood by this one example. So if you only focus on anything, this example should be the one. Okay, so these graph states that we have, you'll see through the rest of the talk, you'll see lots of figures where you've got graphs and vertices, and the vertices correspond to qubits. And if there's no square around this vertex, this qubit is prepared in the state plus. If there's a square around it, it means it's kind of a free qubit, so it can be our inputs to our computation, if we like. And so in the general case of a single qubit, it's alpha 0 plus beta 1. And an edge here means that I've applied a control Z. Okay? So this guy I can understand as a big entangled state, depending on the input state psi. And when I write this guy down, and this is kind of exactly the calculations that you go through when you want to prove measurement-based quantum computation. If you use any review of measurement-based quantum computation, this is the simplest example you can have. If I just do this calculation, in the same way that I decompose my states to see what my outcomes are for the Bell, for teleportation in the Bell basis, if I here, I'm going to measure this system in the basis plus or minus theta. So I just rewrite this state out in this basis. And you can kind of see, so there's no magic here, it's exactly what happens in teleportation, that when I write my state out in this basis, if I've got the plus state on the left, then I end up in this state, and the minus states end up in this state, and I kind of interpret these as two different unitaries on my input state. And this is exactly the interpretation as what happens in measurement-based quantum computation, by the way. So in measurement-based quantum computation, this is exactly how I would implement the rotation through theta on the z-axis. And I would, in measurement-based quantum computation, I don't want this random z to the m, so I undo this afterwards. And that's the feed-forwards process in measurement-based quantum computation. Okay, but you can forget about all of that. All you need to see is that when I've got this graph state here, I've got this entanglement here, and what it means is that when I measure this guy, depending on that basis that I measure this in, I'm going to randomly sample from a different pair of unitaries, um. So this gadget, so the whole kind of technique that we have is we try and find the right graph that gives us the right set of unitaries which have the nice property of being a t-design. Okay? So we take, so our first kind of, I have a couple of sets of results. Our first sets of results is taking this construction that we know works and kind of translating and finding graph state gadgets which implement this construction for us. And then later on we found that actually we can, once we kind of got a feeling for how all that works, we can see that if I take some nice kind of regular lattices that are useful for measurement-based quantum computing, it turns out these are also very good t-designs, and then later we'll see connections to these boson samplings and IQP samplings and quantum supremacy that I mentioned earlier. Okay, so this is the main idea. So most of the rest of the talk, you'll just see these kind of pictures of these graphs. And, you know, if you're really quick at calculations, you can try and prove what I'm going to say about them. But you can just trust me that the role of these graphs is to sample from unitaries in the right way. Okay? So, any questions at this point? No? Good. Okay. Was there a question? No? Okay, so we're going to use, so the general idea now is to extend this idea to bigger graphs, to mimic what happens in this construction of t-designs that I mentioned before, and we'll also use it to find new 3 designs, and then later on we'll use it to find new efficient approximate t-designs which have certain nice properties. Okay, so this is the circuit, so this BHH construction for, remember this is a way of generating circuits which act as t-designs. Okay, so it means you roll a lot of dice. So the way it works is as follows. Okay, so I take a family of universal unitaries. Okay, so this could be, you know, my standard set. It could be my pi by 4 gates, my pi by 2 gates, and Hadamard, and some control not gate. So I take some universal set of 2-qubit gates, whichever one that is. So this construction works for whichever family of universal gates, which is something very nice about the construction. And then I just start rolling my dice. So first of all, I'm going to roll a dice, a two-sided. I'm going to toss a coin. The output is S or 0 or 1. And if I get 0, I'm going to perform gates on kind of even pairs. If I get 1, I'm going to perform gates on the odd pairs. And each of these unitaries here, I'm going to toss another bunch of dice to choose each of these randomly from this set. Okay? So this is how I build my circuit. So my circuit is constructed, and you can see why this is kind of a bit painful if I ever want to implement this, because each time I roll my dice, I need to design a new experiment to see how it works, but this is the idea. But I roll these dice and it gives me this first layer of this circuit. And I repeat this and repeat this and repeat this, and the efficiency, my statement of efficiency of my t-design, is that if I repeat this process poly in nt and log of 1 over epsilon times, I get an approximate t-design for n qubits. Okay? So this is my construction. I've got my dice, and it allows me to write my circuits down, and for any given instance, for any given set of results of my dice, I'll get a particular circuit, and sampling from this circuit is allows me to do all those wonderful things that I started talking about at the beginning of checking entanglement or hiding information or benchmarking, etc., etc. Okay, so the way that we kind of translate that to this measurement-based picture is, first of all, by noticing that I can rewrite this circuit in the following way, which is that I fix the set of systems where these unitaries apply, and I randomly either apply or don't apply this swap, which stops them here. Okay, so that's all that's happening in this redesign. And then the way that we go from this to this measurement-based picture is we just find, in exactly the same way, our graph gadget from before. If you remember our simple gadget, we had a graph with 2 vertices. We performed a measurement in a fixed angle alpha on the first vertex, and it performed for us for free, randomly, either one of 2 different unitaries. So what our task now is to do is to find a construction of graphs with particular measurement angles that are going to simulate this circuit for us. Okay? And so I'm not going to go through the proof of how it all works, but the idea is that we find a set of graph gadgets which randomly sample from a universal qubit gate set, so these guys, another set which do our permute swap, and the kind of most difficult thing in the whole kind of proof was to impose some kind of common dependency on these. Okay, so this S here, you notice, is the same as this S here. Okay, so when I'm constructing my graph gadgets, I need some kind of extra tools to do that. Okay, that's all. And just to give you, and so kind of technically some of the, for those of you more familiar with the field, this permute swap is kind of, once you can do these guys, it's kind of easy because these are all Clifford gadgets, and these Clifford gadgets are much easier to treat. And this, to impose this kind of common dependency, we kind of devised this so-called generalized fusion operation. So for any of you who've worked in measurement-based quantum computing, you'll have heard of these fusion operations. This is like a generalization of that. Okay, so this is just to show you a bit how complicated and ugly these graphs look like. Okay, so we can do it. So we can find this set of individual graph gadgets, give me my Z rotations, my X rotations, and my control Z. So with these, I've got a universal family of gates. And if I combine all of these guys, I get my swap gadgets. I can combine all of these to get my Z rotations, my X rotations, and my swap gadgets, control Zs. And then I can do the same to get my swap gadgets. All of these are just in terms of Hadamard's and control Z, so I can use my previous gadgets. And then the last thing I need to do is kind of, if I look at this example, this is kind of just an extension of our first example. So it gives a single qubit gate, which is Z rotations, X rotations, Z rotations. And you'll notice, so what I mean by kind of imposing this common dependency is that when I do this, each of my angles here depends on a different output. Okay? So we need some extra tricks anyway. We add some more edges. We add another couple of vertices to make sure that these things happen at the same time. Okay, and so what it all translates to is that you can take this construction and you can use it to define a fixed graph state. So I no longer need to roll my classical dice and change my circuit depending on that. I have a fixed graph. It's kind of horrible and looks like some weird combination of all these guys. But it's kind of efficient in the sense that the number of qubits and number of edges is exactly linear with respect to this construction. Okay? Okay, and there's no need, again, there's no need for this classical randomness or associated reconfiguration of my setup. Okay, so this was kind of our first big result in this direction. But it suffered from two main kind of issues. First of all, so it's polynomial, and any of you have kind of heard computer scientists say that that's efficient, should be wary, because polynomial can have massive coefficients inside. And this guy, so it's kind of efficient in the sense of a computer scientist, but if you wanted to build these guys, they're not very efficient, okay? For small n and t, these guys are still quite big, okay? So we'd like examples that, in particular, we'd be able to implement in the lab. Okay, so the first thing we want to do is try and find more efficient versions of these for small n and t. And this graph is rather irregular. And for various reasons that we'll come up to later, it's much better if this guy can be regular. So it makes our experimental setup easier. And it also, in terms of these applications that we'll talk about, it's much nicer if it can be regular because it allows translations to circuit with a constant depth. And yeah, I just got. Okay, so the first kind of next set of results we tried to do was to search for exact designs. That I mentioned, we have some new exact 3 designs. And the kind of technical tool we use for that is what's called the frame potential. So this is just a way of, I'll give you a set of unitaries, can you tell me if it's an exact design? And it is, if this guy is tight on this inequality. Okay, so it's just a way for us to test if our ensemble of unitaries are an exact T design, so exact meaning exactly this epsilon is 0. Okay, and for non-exact designs, this value of this tells you how close it is to an exact T design. Okay, so the first thing we found was that this particular gadget is a new 3 design on a single system. So this is one of the most efficient 3 designs that we have, and it has this very interesting structure with compared to known 3 designs, in that it has these irrational angles coming up, these irrational rotations induced by these measurement angles coming up, which don't appear in any of the other constructions, which are essentially based on groups. Okay, so there is some kind of way of seeing this as a projection of some group, but it's not exactly clear how it's related to the other 3 designs that we know, which is the Clifford set. Okay, and so then we kind of looking at extending the numerics on this. If you extend this line, you see that as L gets bigger and bigger, you're essentially able to do T designs of higher and higher T. And so for all of these examples where we go down to T, this is a much more efficient way than the HBB construction. So if I had the HBB construction for this, it would already contain like 80 qubits. Okay, so it's polynomial, but 80 is much more than 5. Okay, so that's the kind of first set of results. And then more recently with my student Rawad and collaborators in the Lebanese University, we've been able to show that if I take now a regular lattice of my qubits of my graph states, so this sort of graph state here is also the one that's used for universal measurement-based quantum computing. So there's been a lot of work on how to build these lattices, and they're nice and regular, and we've got we know lots of properties about these guys. Okay, and so we were able to show that for fixed angle measurement, so again, I don't need to insert any kind of classical randomness. I can just generate this big graph state, and I do these measurements, and the length of this graph state is poly and nt log 1 over epsilon, so the same order of efficiency as we had from the HBB construction. But now I've got this nice regular lattice structure. Okay, and so the proof sketch for this is essentially to show that each of these boxes here, so each of this graph we kind of decompose into these boxes, and the proof kind of runs along the same lines as this BHH, which is that once you've got your kind of decomposition into a set of universal gates, and these gates, your kind of sub-ensembles contain certain structure, you can relate this to a Hamiltonian problem. You can relate it to a Hamiltonian and showing the gap of a Hamiltonian, and then we can take lots of nice techniques that we know from many body physics, in particular something called the detectability lemma, to allow us to prove that we've got some gap. Okay? And so the particular kind of properties that we want of these boxes is that they are universal for S4. So if I take each of these boxes, this box samples from a set of unitaries on SU4. And you can show that it's universal on these guys, that for every unitary that I get in this ensemble, its inverse is also in the ensemble, and that each of these gates is chosen with equal probability. And once you can do that, when you're looking at the kind of average effect of these unitaries, you can translate that into a Hamiltonian, which we know how to diagonalize and prove statements about its gap. And this gap is what allows you to prove that it's a T-design. Okay. Okay, but I won't go into any more details than that. Okay, so even more recently, so this is now I'm talking about work that's not published, but we're finishing now with Road. Based on some constructions by Juan Bergamo-Vega and collaborators, you can kind of show that not only does this sample from a T-design, but these T-designs in this particular instance also are hard to sample from with a classical computer. So this kind of initial application that I was talking about at the beginning, now I've got this way of sampling from unitaries, which has this nice property of being a T-design. Here we can also see that these unitaries give these instances of hard to sample from computations. Okay? And this kind of really mimics some of these results by these guys in the last year, where they also show similar statements for regular lattices, but their regular lattices are a bit different from ours and have some different properties. Okay. And so our statement at the end of this is that if I take our construction, which is known to be a T-design, it also has this property that if I wanted to try and have a classical computer which simulates the statistics of the measurements that I'm going to receive from this, the only way that it can be efficient, so it's impossible essentially, as long as you assume that two things that computer scientists would very strongly believe essentially. So for physicists, it's like saying as long as you believe there's no signaling or the second law of thermodynamics. But technically the statements are that you should believe that the polynomial hierarchy doesn't collapse to the third level and that the associated worst case sharp P hard problem, so this just means that this sampling is associated to very difficult problems that we categorize as being sharp P hard in complexity theory. And it just says that the worst case instances arising from this sampling is somehow hard implies that the average case is also hard. Okay, and this is really a kind of standard conjecture in complexity theory as well. Okay, so what it says is that a classical computer can't sample from the output distribution in any kind of polynomial scaling. Okay, up to some L2 norm error 1 over 22. Okay. So this statement essentially says that the sampling of this is difficult, and it's the same kind of statement that's made for all of these samplings like IQP and boson sampling, etc. Okay. And so the proof sketch of this, again, kind of comes down to this universal gate set that we used for that was kind of part of our proofs that this is a T-design, also appears here. In that once you've got a universal gate set, you can show that if you're randomly sampling from a set of unitaries which contain a universal gate set, then inside that family there will be a sharp P hard problem. Okay? And so that means it's sharp P hard in the worst case. So sharp P just means really hard, like boson sampling hard, and etc. Okay? And so the next kind of piece to the puzzle was a statement which was proved very recently by these guys to show that once you've got two designs, these guys anti-concentrate. So what that means is that essentially they behave like Haar random unitaries in another nice way, which is a really important part in the proofs of how you prove these hardness, how all the proofs of hardness comes together. And so once you've got these two kind of pieces of the puzzle, you can kind of apply the standard proofs for hardness of sampling, which involves something called Stockmeyer's algorithm. You can see this paper for more references on that. Okay, so this is kind of our construction and its hardness. And so to finish with, I'll just say a few more things about the implications of our construction for circuit versions of this problem and for scattering in a moment as well. Okay, so in the circuit picture, what's happening here is so if I wanted to view this in a circuit picture, what I would do, I would take all my inputs, I would take all these guys. Remember, these guys are prepared all in the plus state, and I'm just preparing a bunch of control Z gates, and then I'm doing a bunch of measurements. Okay, so if I did that in the circuit picture, so the fact that this is some nice regular lattice, and that all of these are control Z, so they all commute with each other, means that I can do all these gates, all these control Z entangling gates, in kind of a constant number of rounds. I just need 4 rounds for a regular lattice like this, in fact. And then at the end, I can do my measurements, which is equivalent to doing a local rotation and measuring in the Z basis. So all of our constructions here for the T design and for the sampling are constant depth quantum circuits. Okay, so this is something that's quite interesting. If Google say they've got this universal quantum computer, you can find kind of quite easy things for them to do in constant time, so they don't need huge memory, they just need to be able to build these circuits of kind of polynomial size and do these measurements. So this is why kind of people are excited by these kind of results, that they allow us to really test these kind of near future quantum devices. So if you could have, so you know, then just kind of for orders of magnitude, if you could have circuits like this with 50 to 100 inputs, which is, we're kind of getting there technologically, you should be able to see these kind of quantum speedups that we're talking about here. Okay, so this is why people are excited about these kind of results, because it says, well, actually, this is how I could test that my quantum device is doing something interesting. Okay, and so another kind of application that I mentioned briefly before was these connections to thermalisation. So it's known that if I've got a 4 design or above, then unitaries. So if I imagine my interaction with an environment being these random unitaries, then if these are taken from a 4 design or above, this efficiently thermalizes my system. And you can translate all of this construction again to a kind of scattering picture where I have these N systems here, and each of my photons or whatever my scattering media are come in through a fixed interaction again and again and again. And as long as there's kind of, with only a kind of polynomial number of these guys, I'll get thermalization close to the Gibbs state. Okay, and so with that, I'll kind of finish off. So kind of overview of what we've seen. We've generated these this approach to generating ensembles of unitaries via these graph states, which are nice in quantum information because they relate to lots of other things like measurement-based quantum computing. And they're in particular well suited for implementation because of this. And we've seen some applications of these in computational advantage or quantum speedup or hardness proofs in scattering and thermalization. I didn't have time to talk about, but there's been also results using these for benchmarking of a measurement-based quantum computer. So in particular for like one of the main kind of proposed schemes for building a quantum computer will be these measurement-based schemes. And if you did it in these measurement-based schemes, you've got this kind of inbuilt benchmarking for you, which was work that was presented by one of my co-writers, Pete Turner, and his collaborators. And we're also looking at kind of using these for cryptography. So again, when I kind of want to hide my information, these T designs give me an efficient way of doing this. Okay, and with that I'll finish. Thank you very much.